Hey, I'd like to finish up this week with what I think is a real fun lecture about the Mandelbrot set that really shows the advantages you get by doing things with fragment programs and taking advantage of all the parallelism that's built into the GPU. Usually, I don't talk about fractals until later in the course, and in fact, I will talk about it more later in the course. And it'll turn out, when you'll see later, is that the Mandelbrot set doesn't quite fit into the other presentations of the other kinds of fractals, but it's sort of obligatory in a graphics course to say something about the Mandelbrot set. And I just realized what a great example it is of the things we've been talking about in the last lecture. So I'll give you just one example of fractals that are more general than the Mandelbrot set. But the thing we want to focus on is that the Mandelbrot set can be computed on a pixel by pixel basis and then really take advantage of the GPU. So let's just, for one example, let's look at our old friend the Sierpinski gasket, which we started with. And the second way that we did it was that we did it recursively and took a triangle and subdivided it into 4 little triangles, threw away the middle, and subdivided each of them and recursed on that as many times as we want. Now, the reason this is not a normal geometric object is that if you look at this, suppose each side is length 1, and so the perimeter has length 3. If you look at the total perimeter of after the first iteration, you have these are each now of length 1/2. So you have each of these triangles has a perimeter of 3 halves. And so you have 3 times 3 halves, or 9 halves, and now that's bigger than what you had for the first iteration. And every time you subdivide, the triangles you wind up with have the same ratio greater perimeter than you did in the first place. So as you keep subdividing, the total perimeter is going towards infinity. Now, if you look at the area, it's pretty clear what's happened is that you have 4 identical triangles here, if this was an equilateral triangle, and you throw away one of them, so the area now is 3/4 of what it was in the first place. And then when I iterate on these 3 remaining sub-triangles, I get 3/4 of each of their areas. And so the area eventually is going to 0, but the perimeter is going to infinity. So this is certainly not a normal geometric object, and it's one of the objects that made many mathematicians see that the normal geometry couldn't explain these objects or model them, and they became called fractals, standing for fractional geometry, because in this case it's neither one-dimensional nor two-dimensional. It's somewhere in the middle, and what we mean by somewhere we'll talk about later when we develop the topic. But the Mandelbrot set is a fractal of a very different type. And we'll start off by looking at numbers in the complex plane. So let's take a totally different approach. And I'm sure that you've all seen this from high school as well. What is a complex number? We can write a complex number as a real part plus an imaginary part, where J is something that if it was squared, it would give you -1. But we could, each xy point in the complex plane forms a complex number, and the standard operations of addition and subtraction in the complex domain are if for addition you sum the real parts, and that gives you the new real part, and you sum the imaginary parts to give you the new imaginary part. The product is a little bit more complex, but if you use J squared equals -1 and you simply multiply out x1 plus jy1 times x2 plus j times x2 plus jy2, the j squared gives you -1, and you get this form for multiplication of 2 complex numbers. The only other fact we need here is we're not going to need conjugates for what we're doing, is you need the magnitude. And the magnitude is simply if you have a point in the complex plane given by x plus jy, its magnitude squared is x squared plus y squared. That's all we're going to need. Now, you can talk about complex functions that take a value of z and apply a function to it and produces another complex number. So if we look at that for a given function, what we do is, so the first time I apply it, I start off with some complex number z0. I apply that function to it. It gives me a new value z1. And if I keep iterating on that, so I keep sticking the new one back into the function, I get z2, z3, z4, and so on. And that traces out some sort of a curve in the complex plane. Now, a number of things can happen. As we keep doing this, going towards an infinite number of times, one of three things could happen. These points can go off to infinity, and the whole thing diverges. These points can converge to a single point, sometimes called an attractor, or they might just repeat. Like if, for example, you were on a circle in the complex plane, you could have a function that simply goes around and around. It's a rotation, and it neither converges to a single point or goes off to infinity. So that's the basic idea of functions in the complex plane, and that's now let's look at how we can look at one particular function that's going to generate the Mandelbrot set. So suppose I take this very simple function where c is an arbitrary complex number, and I start the iteration off with z0 equals z plus is just the origin in the complex plane, and I iterate this function. So the next one is given by squaring this one, adding on the constant, then I take the result, I square that, and I add on the constant again. And we have two cases that are going to happen. One, that as k gets large, the magnitude of the function goes off to infinity, and the other option is that it remains finite. So in principle, at least, I mean, evaluation, you can't do this analytically, but you can do this numerically for any c that you want. If for a given c, it doesn't go off to infinity, it stays finite, then we say c is a member of the Mandelbrot set. So if we now were to take a plane and let's rule it into pixel-sized areas, and let's let each c be the center of that pixel. Now I have a way of computing members of the set computationally, but numerically. And so I can, for all the c's that are now the location of pixels in that rectangle, what I'm going to do is apply this function and see what happens, whether it's going to blow up or it's going to remain finite. Now, I mean this in the sense that we may not be sure. We may do a lot of iterations and not be sure if it goes off to infinity or not. But we can. This is some of the most interesting features of the Mandelbrot set occur when you're not sure of what the eventual result is. So let's look at the computation very quickly. So we pick a rectangular region, and each pixel now has a value in this region. You could talk about, say, starting off with a box that, say, goes from -1 to 1, 1. Probably we're better off, say, starting off at something like -3 to 3, 3. You can take any box you want, and now you can figure out the mapping of that to pixels which go up to, say, 0, n, and 0, n minus 1 in both x and y. Where n will determine how great a resolution you want to compute this to. That's a very simple scaling and translation operation. So for each pixel, which gives us the value of c, we do this iteration. And one little fact that we need, which will help us, is that we keep checking the magnitude. And if the magnitude ever gets greater than 2, or actually we check the magnitude squared, and if that gets bigger than 4, we know that that point is going to go off to infinity, and therefore that starting point, the value of c, can't be a point in the Mandelbrot set. And if we do a lot of iterations, we can sort of look at small ones that stay very small and say, okay, they're probably going to converge, and we'll say they are members of the set. So we can assign a black and white to them depending on what that magnitude is. So very small magnitudes will give us 0. Things that are greater than 2 are going to give us 1s, or when we convert them to grayscales will be white, and the ones that are close to 0 will color black. Now the interesting ones are where we're not sure. We do a lot of iterations, and magnitude is not going to infinity, but it's still not going, we're not sure it's going to 0. And so what we're going to do with those is we're going to assign them shades or eventually colors that are between, at least in the black and white case that I'll show you first, that are between black and white based on how large that magnitude is after some number of iterations, 100 iterations or 200 iterations. And we do that for each point. And so for that rectangle at that resolution, we're going to get black and white points that we're sure in or sure out, and then grays for points that we're not quite sure of. So here's a black and white Mandelbrot set. The most interesting part, the origin is about here where my cursor is, and probably the most interesting region is somewhere over here. Now look at what's happening. First of all, this very far off view of the set, it shows a lot of interesting features. There's little points out here that may be in. There's if you look at this in a higher resolution, you'll start seeing points along this axis, but not connected to each other. And the most interesting parts are when you start blowing up these regions. So you can say, well, wait a minute. If this, say, is -3, 3, and this point up here is maybe 1 + 3, and I said, well, I want to look at this area in more detail. As I start blowing it up, it doesn't really resolve the problem. In fact, it starts revealing more and more detail and incredibly beautiful and interesting shapes. And that's really the interesting part of the Mandelbrot set. It's sometimes called the most complex object known, but on the other hand, it can't be very complex because it's generated by a very, very simple equation. So it's a very, very interesting object in a number of ways. Our view is going to say, let's just look at trying to generate this, and I'll eventually give you a little interactive program for doing that. So the most interesting points are over here. They're in the starting around, if you start centered at around -0.50, you'll get some interesting results. But it gets more interesting if what we do is now try and color those points. That instead of showing them as gray, we show them as colors. We do some of the things we did in the last lecture. In particular, rather than color these as gray, we use some sort of mapping to get nice colors out of that. And a lot of the things you see with Mandelbrot sets are based on using different color mappings from the grayscale. And then as we said, we keep zooming in on certain areas to look at this detail. So here's one example of where, let me come back here, where we look at one of these areas around here and blow it up a little bit. And here's a picture of starting to blow up the one on the this is the one I think on the left edge. And notice even at this resolution, we keep blowing it up and blowing it up. You get points that you're pretty sure are in, points you're pretty sure are out that are gray here because of the background I put on, and then more and more detail being revealed where you're not sure it's in the set or not in the set. And this wonderful little detail over here. So how do you do that? Well, let's look at the JavaScript part of this, and then we'll look at the fragment shader. Okay. As usual with these kind of imaging problems we've been showing you, the JavaScript file is pretty simple. The only difference is if you look at I have two programs on there, Mandelbrot 1 and Mandelbrot 2. They're under chapter 10, I believe, because I discussed fractals in more detail then. But the things you want to pick are the size of the window, the height, its height and its width. You want to pick the number of iterations you're willing to do, and the size of the image you want to generate, and you're going to make that a texture because we want to display these things as texture. So this is, there's not much here except setting some parameters and starting a new image as unsigned bytes. Okay, a little bit more here. I'm going to give you two ways. Now this was the traditional way of doing it. What you did is you generated the Mandelbrot set by a very simple C-like program. Here it is converted to JavaScript, which simply does the iterations. Here's the scaling to get it from units in the in screen space into x and y's and in the range that you want. And here's the computation. This is the complex computation where the complex variable is stored in C, in a little array C, which just has two values, 0 and 1 for the real and the imaginary part. And this is the simple calculation of that function into sticking it into a complex variable C, which is, this is the real part, the imaginary part. And here's the check to see if the magnitude squared is bigger than 4, then you're going to get out of the loop and say it isn't part of the set. So it's exactly what we were talking about. And the problem with this is oh, and let me give you the rest of it here. Is now here's assigning gray levels based on the magnitude. So this is the standard way of doing it. Here's a little color map that's using some sinusoids based on the value that you get out. Here's if the magnitude got greater than or equal to 1, you clamp it to 1, and that'll turn out to be the maximum gray or white, which then gets mapped by this into colors. Okay, so now what do you have to do to display this? You do exactly what we did in the last couple of lectures. We define a rectangle out of two triangles, and then we set up a texture object using this as the texture image, and then we simply render the triangles. So here's a simple example. This program is under chapter 10, and I think it's called Mandelbrot 1, and here's the values. And if you go back into the code, you can easily change the values of that affect the size of this and the scaling of this, and it's easy. And then then we said, well, wait a minute, this is not the way you want to do something. You really say, if you look at this, here you got this big iteration going on over x and y. It's doing lots of things, and it's doing it in the CPU, so there's absolutely no parallelism going on. You're not making use of the graphics to do anything except put up a texture map. So this is really, if you think about it in terms of what we're doing now, is actually a very terrible way to go about it. So let's look at another approach, which is much better. This is incredibly inefficient, and let's look at this. So if we look again at the calculation, it's the kind of calculation that a lot of people in parallel processing call embarrassingly parallel, because there's no relationship between adjacent values points that you're computing or values you're computing. Every fragment that you're computing is completely independent of every other fragment. So there's really no reason to worry about the loops if you're sending the geometry, the rectangle, to the vertex shader and then generating those fragments. Those points are being generated automatically for you. So why not do this computation within the fragment shader and don't go over any loops in the JavaScript file? In fact, all the JavaScript file has to do is send over that rectangle, and everything happens in the fragment shader, because the fragment shader, each fragment knows where it is and then can determine its own color. So if you look at that, we can make it interactive very, very easily, and the program Mandelbrot 2 does that, and I'll show that to you in a couple of minutes. So what I did in that was to get the window parameters from sliders that we put in the HTML file, and I think I kept always kept it square, so you really need just one slider to change the size of the square that you're looking at. And we don't even need the texture map, because all we're doing is working on individual fragments, and they each generate a pixel, so I don't need a texture map as part of this at all. So I'm not even going to give you the application or give you the vertex shader, because they're kind of trivial. The only interesting part is we put this in the fragment shader. So here's the fragment shader. It's going to have get in the size of the array and a scale factor here as a uniform variable sent over by from the application, and the application can have these values changed through the sliders. And then here's really the interesting part. This value pi is used just to get the colors. I'm going to do at most 100 iterations. I'm going to make this 1,000 by 1,000 array. That's at least to start with. And now here's the calculation. Now this is again the scaling to get from units in window coordinates into x and y's in terms of the iteration Mandelbrot shader, this is exactly that calculation. It goes up to the maximum number of iterations. It computes here, I'm using different variable names, but this is computing the next complex value from the equation, computing its magnitude squared, checking if the magnitude squared is greater than 4, essentially exactly what we did before. And if it's greater than 4, then we can stop iterating. So let me sort of finish it, and here we assign colors using some sine and cosine functions just to get some nice colors, and we're clamping it if it's bigger than 1. And notice here I can use the min function to clamp rather than using an if then else over here. So this is the standard way of computing. Here's I'm using sines and cosines to get the green and the blue, and just reflecting the red component. Okay, now notice here that there's no iterate. The big loop on the outside in x and y just isn't there. Why? Because the x and y are coming in here from GL frag coordinate. That's where you get, I mentioned this in the last lecture, that you always have this available to get you where in screen coordinates that fragment is that you're working on. So you get those fragments, scale it, and translate it as you need to get into the correct units for the calculation of the Mandelbrot set. So that's it. I mean, there's essentially nothing there. Now, now, if you look at that closely, it gets much more interesting because look, what is it going to do? You've sent over a rectangle. What happens? That rectangle is being rendered and generating from the rasterizer is generating these fragments. It's generating these fragments as fast as it can. So if an iteration stops because the value of the magnitude squared was bigger than 4, what happens? Well, you've now colored that fragment, and now the GPU says, well, give me the next fragment. So this thing is working with a lot of concurrency of fragments going on independently of each other. And the more fragment processors that are present inside of your GPU, the faster this is going to work. So compared to what we did with the first example where we did everything in the CPU, here you got an enormous amount of parallelism going on because of the multiple fragment shaders. The GPU is much faster in general for doing this floating point operation. And if you were going to be really clever about it, you could probably do 4 in each fragment calculation because really you're generating a gray level that gets mapped. But if you're generating only a gray level, then you're really not taking advantage of the fact that the red, green, blue, and A components could also be computed and generate 4 fragments at the same time. So you could really be a little clever. But even here, this could be anywhere from 4 to 100 times faster because you might have anywhere from 4 to 100 or even 1,000 units all working on different fragments. So let me finish this then by showing you kind of a kludged up little example that I did. And you certainly feel free to make it much nicer, but it's going to really just show you how, and I made it a little too small probably, but this just shows you how fast this is computing. This is, I'm going to be doing this real. So what we're going to do is we're going to just move around a bit, move it around, scale it, make it a little bigger. Here, I see I don't have the scale factor going enough, but you can sort of get the idea that I can move the Y around, I can move the X around, I can scale it up a little bit bigger. I have a couple of versions of this, and I think I have another version that's even better than this one. But you get the idea. Just notice here just how fast that's computing because it's all being done within the GPU. So fool around with this one. If you have a better version, send it to me and I'll post it.